Hello, everyone. Today, we're going to continue our discussion of production externality. In the previous class, we stopped in the middle of interpreting the first order condition. So, we'll get back to it and then move on to a new chapter, which is about public goods. Okay, so let's go to the notes from the previous class. Okay, so here we were talking about how to find the socially optimal level of pollution. So we assume that the two firms merge and operate essentially as a single entity, right? And then we wrote down the profit maximization problem for the merged firm, which produces not only steel but also fish, right? So this is revenue from steel and fish and the cost of producing steel and fish. And then we derived this first order condition. So assuming that the solution is in the interior, we had all of these conditions holding with equality, right? So the solutions are indicated by these double stars, right? And then in particular, this condition about X, remember X is the quantity of pollution produced by the merged firm, right? And it says the first condition says zero should be must be true at a solution, and rewriting this I can have this minus this much, and this one can be interpreted as the marginal private benefit of pollution to firm 1, and the second term is the marginal private benefit of pollution to firm 2. I mean, here I use the language firms 1 and 2 because this is something that accrues to firm 1. I mean, if the two firms were separated, then this would be what would accrue to firm 1, and this is what would accrue to firm 2, right? So I will continue from there. So let me copy that. All right. So I may try to rewrite this even further. So on the left, I will keep only this term and move this guy to the right-hand side. Okay, so here now remember this is the cost, and remember that as x increases, from 2's cost of producing fish actually increases, right? So this right hand side can be interpreted as marginal private cost. So that's marginal private cost of pollution to firm 2, right? So, I mean, the only difference between this guy and this guy is that I've changed the sign, right? And I know that this is positive, then this can be interpreted as cost. And if once I put minus symbol here, then the whole thing becomes, so I'm changing the sign of the quantities that we are talking about, and this can be interpreted as benefit. And the reason I interpreted it in this way was because here, this term is positive. So when I wrote the equation in this manner, the focus was on the first term because I know that the first term together with this minus symbol, this is positive, right? So I wanted to compare everything in terms of the sign of this guy. Anyway, this is the marginal private cost of pollution to firm 2, and this one is marginal private benefit of pollution to firm 1, okay? But if you view the whole thing from the society's perspective, this one can be viewed as the marginal social benefit of pollution to the society, so I don't have to specify whether it is from 2 or from 1. Okay, and on the other hand, this right hand side is actually marginal social cost of pollution. Okay, so the distinction in my language between private and social is that private includes only one of the two firms. Okay, but here social means is a concept that applies to all the firms in the model. Here there are only two models. Here in our model there are only two firms, and therefore this marginal social cost would include the cost of pollution to firms 1 and 2. But there's only this cost to firm 2, right? Firm 1 does not incur any cost from pollution. In fact, firm 1 gets this benefit, right? And therefore, this marginal private benefit of pollution will be actually the marginal social benefit of pollution, because firm 2 does not get any benefit from the pollution, right? So these two guys, social, they mean including both firms 1 and 2. Okay, so the condition we get eventually is that marginal social benefit of pollution should equal marginal social cost of pollution. Okay, so that's what the first order condition, this first order condition would say. Okay, and you may wonder how this condition relates to this. So here, so let me explain this. So here, marginal private benefit to firm 1, that is, we know that this guy is, by our assumption, this guy is like this. And on the other hand, this together with the minus symbol, this guy is negative, right? So what we are actually calculating in this equation is some non-negative number plus some negative number, right? And therefore, what we are effectively calculating as we add up these two guys is the net marginal social benefit, right? So if you want to kind of be super specific about the signs of the terms, what we are calculating here is the net marginal social benefit. On the other hand, when I write these things in this way, this one, I know that this one is non-negative and this one is also positive by our assumption. So we are comparing two positive terms on two sides of the equation. And the first order condition says, well, the two things then should equal. Okay, and this is not so surprising because if you think about what would happen if this equality is violated, okay, suppose the left-hand side is larger, okay, so marginal social benefit of pollution is larger than marginal social cost of pollution. That means as you pollute one more unit, you get a larger amount of benefit than the cost to the society, and therefore in that case it is desirable, welfare enhancing, to pollute a little more. Okay, and therefore the current level of pollution is not optimal. If this is true, so then if you pollute more, then there is this much cost which is larger than the benefit of pollution, and therefore you should actually decrease the pollution to increase the social welfare, right? And again, this says that the current level of pollution is not optimal, right? So the arguments that I just gave tells you that, well, at a solution, these inequalities would never never be the case, and therefore we should have this much at a solution. Okay, so now let me try to indicate these, illustrate these, how the solution would compare from the merged case to the case where the two firms operate separately. So on the horizontal axis, I'm going to measure the amount of X, the pollution. Okay, and on the vertical axis, I'm going to measure basically the dollar amounts, these marginal benefits and cost of pollution. Okay, and so we would have these two guys. Okay, let me make them intersect here. Okay. Okay, so currently, this marginal social benefit of pollution. Okay, so I'm trying to indicate these guys. So marginal social benefit and marginal social cost. I'm trying to indicate these guys in this space. Okay, and so we have this, and on the first graph is, right? And we saw that at a solution, this minus partial C1 with respect to X, that should be equal to this guy, right? In other words, this graph and this graph should intersect at a solution. So here we have the intersection. If you go straight down, then this will be X double stop, right? So just to rewrite, so this means basically marginal social cost, right? And this downward sloping curve is marginal social benefit, okay? And we want to find X double stop, optimal amount of pollution that equates marginal social benefit with marginal social cost, okay? And they intersect here, okay? So that's what happens when the two firms operate as a single entity. But what if the two firms operate independently? So for that, let's go to the notes from the previous class. Okay, here we saw, okay, here. So what is the level of pollution when the two firms act in a self-interested manner? And we saw that at a solution, firm 1 would choose X star so that this is equal to zero, right? And to rewrite this, this means that 0 is equal to that, right? So remember that together with this minus and this much is marginal social benefit, right? So to indicate that in this figure, when the two firms operate as different independent entities, firm 1 would choose X so that this guy is equal to 0. That means you choose X when this graph intersects with the horizontal axis. So this point is X single star, sorry. And you see that the first quantity is smaller than the second quantity. Okay. So, and of course, there are some assumptions we are making to indicate these two values in the same space, and so the assumptions, just in case you're curious about what kind of assumptions we need. So first of all, this guy, remember that this C1 is a function of what? Steel and pollution, right? And this this partial derivative, I'm assuming that this partial derivative is independent of s. That means this guy depends only on x. Okay, and another thing is that this guy should also be independent of the amount of fish. So independent of fish. Okay, and only in that case the changes in S or F would not affect the relative positions of these two graphs, and therefore we can write down the positions of x double star and x star in this way. Okay, and in particular, so I want to argue that the solution from the case where the two firms operate independently, so this solution violates the first order condition for the merged firm. So to see that, so suppose that we plug this solution into the objective function. So this pi, okay, that pi is what? Where is it? So that's the profit for this merged firm, all right? This whole thing. That's pi, okay? And one of the first order conditions was this guy. And how did we get this? We differentiate this pi with respect to x and then set it equal to 0, right? So this is what we need together with this. So now let's see if this condition is satisfied when the two firms operate as independent entities. So this would be then, if I just rewrite, have this much, and I know that the first term is 0 because we saw this when the two firms act in a self-interested manner. Firm 1 would choose x so that this guy is equal to 0, right? So this much would be 0. Then the whole thing just reduces to the second term. Okay, and I know that this guy is positive, and therefore the whole thing is negative. And remember that the first order condition requires that this guy should be equal to 0, but it is not, as you see here. Okay, so all right, good. Now, so it's a pity that I have to record this, pre-record this lecture, and therefore cannot really solicit any questions from you guys. But if you have any questions, when we get to meet next Thursday, I mean this coming Thursday, please feel free to ask them. Right. So now let me move on to chapter 37 on public goods. So first of all, the purpose of this chapter is to introduce you to what are key features of public goods and see how the consumption would be individuals' consumption would be affected in the presence of public goods. Okay, and public good in Korean 공공재, right? And examples of public goods are fairly easy to find in real life. For instance, say national security. So in our country, we have military armed forces that protect us from bad guys, and even if I don't really want to have that security for myself, as long as the security is provided to all the people around me, then I will be benefiting from the service, right? And this basically means that it is impossible to exclude just me from getting this public good, right? And some other examples of public goods like infrastructure. So, for instance, if roads are well maintained, everyone living around those roads will be able to use it. And I mean, sometimes you can put kind of a barrier to using the roads, but most of the time we don't have such barriers, and therefore it is impossible to exclude anybody from using the roads. And two key features of public goods are non-rivalry and non-excludability. Okay, non-rivalry means that if somebody uses the public good, such as the national security, that does not really compete with my consuming this service. In other words, even if my neighbor enjoys the benefit of having national security, my benefit of having national security will not be decreased at all. And therefore, there is no rivalry in consumption among the economic agents. And the second one is non-excludability, meaning that it is impossible to exclude some agents from consuming the public goods like national security or infrastructure. Okay, so now the question is then, if there is a public good, then what kind of incentives will individuals have? Will individuals have enough incentive to contribute to the public good? Okay, and our common sense tells us that, well, given these features of the public good, if my neighbors or my fellow citizens contribute to good national security, then I would probably want to free ride, because even if I don't contribute, there is enough contribution from my fellow citizens, and therefore I will still be able to enjoy the benefit of national security because of these two features, right? So that's kind of the intuition we have about public goods, and I want to show that this is actually true in a more formal model. And for that purpose, I'm going to give you a simple game called the public good provision game. Okay, and I will show you that in this game, people have incentive to under-provide the public good. In other words, they will have the incentive not to contribute to the public good as much they would if they are the only one in the economy. Okay, so first of all, the terminology says that it is a game on deciding how much of the public good to provide. Okay, so let me present the model. Hold on, let me get some water. So there are two goods. So one good is the usual good, and just to distinguish it from the public good, we're going to call it private good. Okay, and this is called X, and the other good is the public good. And the amount of the public good is big G, right? And there are two players, 1 and 2. And again, this is to just to simplify our model. The results we will derive in the end will actually holds even if there are more players than just 2. Okay, and these two players have some amount of money which we call the wealth, and the wealth can be spent on one of these two goods. So take any player I. So player I has some wealth, WI, okay, and this is some positive amount of money, and that can be spent. This can be spent on the private good and the public good. Okay, so just to introduce the notation, xi is i's consumption of the private good. Okay, and gi is player i's contribution to the public good. So here I say it is player i's contribution because eventually the amount of the public good will be will depend on the contributions from both players. Okay, so here I said this big G is the amount of the public good, right? So then big G is just the sum of the contributions from the two players. So if you think of this G as kind of the say individuals' tax payment to support some public projects like building roads or building infrastructure and maintaining security forces and so on, then the individuals are determining how much they're going to contribute to support those public projects. And the amount of the public good will depend on the contributions from the two players, G1 and G2. Okay, and so here I said player I is born with this much of money, right? And therefore, player I's budget constraint is that his consumption of the private good and his contribution toward the public good cannot exceed this amount of money he has, right? So I is budget constraint. That will be xi plus gi cannot be larger than his wealth. Okay, and here so here I don't really specify the prices because you may think of these as all of these guys as dollar amounts. So this is WI dollars that player I is born with, and he will spend this much money on the private good and this much money to contribute to the public good, right? So you may think of this as the prices of the private and the public goods being normalized to 1, right? So you may assume that here you have the price 1 and, well, this looks ugly. So let me rewrite this. So xi, 1 times xi plus 1 times gi, like this. Okay, so the prices are all the prices are normalized to 1. Now, what about player i's utility or the payoff? Well, he has a Cope-Douglas utility function, so okay. And what is this alpha I? It is some fixed constant between 0 and 1. Okay. So notice that this in this utility function, it is big G rather than small gi, right? So and big G comes from not only player 1 but also player 2. So if we're talking about player 1's consumption depends, player 1's utility depends on his consumption of the private good, and the public good, big G, that depends also on the contribution by player 2, right? So, and then the functional form is the usual Cope-Douglas one, okay? And of course, whenever, as is the case, whenever we have this kind of log utility function, we define log 0 equal to minus infinity. That means that at a solution, we will never have xi or big G equal to 0, because in that case, we will have just minus infinity for player i's utility, right? Okay, and so now, so as for the timing of the game, players 1 and 2 choose x1 and g1. So that's for player 1. And for player 2, x2, g2, they choose these pairs simultaneously. Okay, so it is a simultaneous move game in which there are two players 1 and 2, that choose x1 and g1 and x2 and g2. So these are examples of strategies for the two players, right? And then what about their payoffs? Well, their payoffs are determined by this functional form. Okay. Now the question is, so how much of the public good will be provided when the two players act in a self-interested manner? In other words, when they just act independently. So what will be the level of the public good in a Nash equilibrium? So let me state the question. What level of the public good is provided when 1 and 2 in a self-interested manner? Okay, and as I said at the beginning, the intuition is that here in this functional form, big G, that is G1 plus G2, right? So from player 1's perspective, even if player 1 chooses G1 equal to 0, he can still get some positive amount of G2 from player 2, right? And therefore, assuming that G2 is some positive number, player 1 has an incentive to reduce this G1 so that he can actually increase X1 a little more, right? That means as player 1 makes its decision, it faces the incentive to reduce G1 because there's always the opponent who's going to provide some amount of G2, right? But then if you apply this kind of argument to the other player 2, then player 2 also has the same incentive. Player 2 would expect that, well, my opponent, player 1, will provide some positive amount of G1, so then why would I increase G2 a lot? Because if I do that, then I will have to sacrifice this private consumption part, right? So overall, you would expect that these this kind of reasoning would take the two players to providing not so much of the public good, right? And our question is to actually show exactly what is the amount of the public good that is provided, and is that socially optimal or not. Okay. So now let me try to answer this question. So we will eventually, although I didn't put it exactly in this statement of the question, what we are asking is basically what is the level of Nash equilibrium when the two players act in a self-interested manner. So the steps for identifying Nash equilibria are, this is something we have done many times. We first of all derive the best response for each player, and then see where the best responses intersect, right? So step one. So find player one's best response. So suppose from player one's perspective, there's some G2 that is given to player one, right? Suppose some G2 is given. Now, player one should solve the following. So it needs to maximize its utility. So first, the player one will try to maximize its utility by choosing x1 and g1, right? And so this is player one's utility function, and the constraints are what? x1 and g1. So this is total consumption that cannot exceed what player one is born with, his wealth, W1, right? And then what about big G? Well, that is just the sum of the contributions from the two firms, two players, right? So I can write it this way. And if I rewrite this, G1 is equal to a big G minus G2. So then now I will plug this into this inequality and then rearrange. Then what do I have? x1 plus big G minus small g2, but I'm going to put that on the right hand side so that I have something like this. Okay? And then now, so effectively what I have done is, using this constraint, I've got rid of this G1 in this constraint, right? And the reason is that small g1 does not appear in this objective function, okay? So then if I rewrite the whole problem, I have the following. Okay, so previously we had this condition that G1 should be non-negative, right? And if that's the case, big G will be always greater than or equal to this small g2, right? And therefore we have this condition, okay? And this, and so here what is nice about this new statement of the problem is I have a big G appearing everywhere, and that helps as we try to solve the problem. So I will eventually go over an algebraic solution of this problem. But let me first try to get your intuition for what the solution would look like. And that is by, first of all, distinguishing whether this condition would hold with equality or not. In other words, if the second constraint is binding or not. Okay, so here I have x1 on the horizontal axis and big G on the vertical axis. And this is the budget constraint, and it is just what? Here the prices are all 1, and therefore it is a line of slope -1 with this much intercept, right? So if I have that, so first let me indicate it with this dotted line. So the slope of this guy is -1, right? And so if we don't have this kind of constraint, so by the way, the intercept is W1 plus G2, so let me indicate that too. So this one is W1 plus G2, okay? So if there is no constraint like this, then player 1 will try to maximize this utility subject to this much budget constraint, right? But now we have this big G being larger than or equal to G2. So we should indicate that. So suppose that small G2 is here. Then our budget constraint is that X1 and G, they should be non-negative, and they should be within this kind of triangle, and moreover, big G should be larger than this. So big G should be always above this. That means that the budget constraint, so it will be only up to this much. Okay, and so in the usual case, we would have this bottom part of the triangle as well, but that is not included in this budget constraint because of this condition. Okay, so the budget constraint is really this much triangle. Okay, and then other than this fact, the utility maximization is as usual, right? And I need to draw many indifference curves and check where the indifference curve representing this utility function is tangent to this budget line. And there are actually two cases. So let me first suppose that this constraint is not really binding at a solution. That would mean that if I were to draw indifference curves, then my indifference curves are like this, and then the one that is farthest away from the origin is touching this budget set at this budget line. Okay, and here you see this is a solution. So that is what? X1 star and G star. Okay, and here we have the usual tangency of the indifference curve with this budget line, right? But if this if this G2 is kind of too big, say all the way up here, then we would not have this kind of tangency. So then, suppose I have, that's too small. So suppose I have G2, okay? So the distinction between these two cases is that here G2 is small, and on the right hand side G2 is kind of large. Okay, then in this case this kind of blue triangle will be very small. So I will have, I will have this, only this little segment, and then the budget constraint will be this little triangle. Okay, so if I were to draw the same kind of indifference curves, what happens is that the indifference curves are never tangent to the budget line, but rather it is, so let me do it again. So this is one budget line, sorry, one indifference curve. And another indifference curve, the one that is farthest away from the origin happens to be passing through this this truncated part. Okay. I think I haven't used the term. So, by the way, this kind of budget set can be called a truncated budget set. Truncated budget set, because this part has been just removed, right? And now the truncated budget set is kind of too small so that the indifference curve is never tangent to this guy, this budget line, but rather the solution is at this corner of the budget set. Okay, so here we don't have the tangency of this indifference curve with this budget line, right? So a proper solution to this problem should take care of these two cases. So how should we do that? So, since we are doing all of this in a pre-recording, I'd like to go over the solution algebraically too. So how should we set the Lagrangian for this? First, I need to write down this objective function and these two constraints in the Lagrangian. So first, the Lagrangian multiplier for the first constraint. Okay, so this lambda and mu, these guys are Lagrange multipliers. Okay, so how to get the solution? Well, you need to, so what are the choice variables? So here I have x1, g, and the Lagrange multipliers too, right? So we have to differentiate with respect to those four guys, Lagrange multipliers and mu. Okay, so first, with respect to x1, x1 appears here and only here. So what I will have is alpha 1 times 1 over x1 plus lambda. Then I have minus 1. And we should set it less than or equal to 0 with equality if x1 is positive at a solution, right? And here I'm trying to be super careful about the first order condition. In the end, I know that at a solution, x1 and g will never be 0, right? Because if these guys are 0, then we will have minus infinity for player 1's utility, and that it will never be optimal. So what we know from this, so it says this must be holding with the equality if x1 is positive, and indeed this is true at any solution, and therefore we can say that this is the equality, and that gives me what? Alpha 1 x1, that is equal to just the lambda. Okay, and then now differentiate with respect to g. And big G appears where? Here and also here. So lambda minus 1 plus mu times 1, that is less than or equal to 0, with equality if big G is positive, and I know that big G is always positive at a solution. So this is equal to lambda minus mu. Okay, now let's differentiate with respect to Lagrange multipliers. So differentiating with respect to lambda, I will have only this. Okay, and the Lagrange multiplier is now negative, and the product of these two guys is equal to 0. Okay, so remember that this is the complementary slackness condition, and it means that whenever lambda is positive, the constraint should hold with equality, right? So one of the two things should be 0. And now with respect to mu, I have big G minus G2 larger than or equal to 0. Multiplier should be non-negative, and the product of these two guys should be equal to 0. Okay, let me get some water. Okay, so our goal is to solve this number 1, number 2, and these conditions, number 3, and this number 4. Okay, so I need to solve these 4 equations slash inequalities simultaneously. Okay, and the trick is to basically, so as we saw in this picture, I mean, usually this is kind of, these pictures should give you some intuition as to what the solution, what will be the nature of the solution. And we saw that the nature of the solution will depend on whether this constraint is binding at a solution or not. Here, the condition that big G should be larger than or equal to G2, that is not binding at the solution, but here it is, right? By the way, here I didn't indicate the solution, but this is the solution, right? So this one is x1 star and big G star. Okay, so let's try to solve. So case 1 is when big G star minus G2. Okay, hold on. Big G minus G2 is positive at a solution. Okay, then by this complementary slackness condition, if this is strictly positive, then mu should be equal to 0, right? So by equation number 4, we have mu equal to 0. And that is good news, because if I have mu equal to 0, I know that this will simplify, okay? And moreover, this Lagrange multiplier lambda will be positive. Why is that? So if this is not positive, then what it says is that solution is located strictly within this triangle, not on this surface, but in this interior. And we know that it is never the case. Even in this case, the solution never lies in the interior of the triangle, right? So here, the only distinction is whether this solution is on this corner, at this corner, or on this side of the triangle, right? So I know, I mean, by our experience, and we know that this lambda is always positive. So this will be equal to 0. This expression in the brackets. Okay. So anyway, combining all of these. So first of all, by 1 and 2, what we have is x1 alpha 1 equal to lambda equal to big G 1 minus alpha 1. And then I can use the fact that these two guys have now been equated, right? And this solving this for G, I have big G equal to this much. Okay, now by equation number 3 and the fact that lambda is positive at a solution, what do we have? We can now have, we can now plug this into this guy equal to 0. So 0 equal to, let me write it in this way, big G, and I know the expression for this guy. I have this. So, and then simplifying this, you would get eventually x1 star. Now we have a solution, so let's put a star there. X1 star is equal to alpha 1 x W1 plus G2. Okay, then big G star will be what? Now you plug this guy into here, right? So plug this guy into here, then you will have what? Alpha 1, they cancel out. So we have 1 minus alpha 1 times this much. Okay. So this is the solution when this much is the case. But we have this big G star equal to this much. So to satisfy this assumption, we should require that. So to satisfy big G star minus G2, we need to require the following. So 1 minus alpha 1, W1 plus G2 minus G2 larger than 0, right? And this is an equation, inequality involving G2, so I can solve for G2, and what you have there is that G2 is smaller than this much. Okay? So to summarize, if G2 satisfies this condition, then the solution will be x1 star equal to this much and big G star equal to this much. This is the solution. Okay, and of course, I mean, I haven't fully figured out what the values, solution values of lambda and mu, but for our purpose, that doesn't really matter, because eventually what we need is just x1 star and big G star. Okay, and case 2. So when G minus G2 is equal to 0, okay? And that's when big G, I mean, in other words, big G is just equal to G2. And when would that be the case? Well, whenever this G2 is larger than this threshold, okay? So remember that. So here we are requiring G2 to be small enough so that it does not exceed this threshold, right? And this, that is the same intuition we got from this picture, right? So we saw that this would be true. So slope of this buzzer line will be equal to the slope of this indifference curve when G2 is small enough. And if that's not the case, if G2 is kind of too large, then we have this corner solution, right? So here, as you see, the value for G star will be what? This value precisely, right? So let me add that here, where this big G star is equal to actually G2, right? So then, so to continue writing, so I can say now big G is equal to G2, and what about x1 star? Well, I know that, so given, where was it? Yeah, here, given this constraint, so the constraint is that this guy is actually equal to 0, and big G is equal to G2, then x1 should be equal to W1, right? So x1 is W1. So if I were to add by equation number 3, okay? So just to make connection with these two pictures, this case 1 refers to the first picture, and case 2 refers to, this second picture. Okay? And so then how do we write down the answer to this question? And so we need to find player 1's best response, right? And it depends on whether this G2 is kind of too big or not, right? And if small g2 is less than or equal to this, less than this threshold, then we will have big G equal to this and x1 equal to that. And for our purpose, what is more important is to find player 1's choice of contribution to the public good, right? And so how do we find that? Well, remember this, so let me add in green. And so this big G star is player 1's optimal choice plus G2, right? So I need to equate this guy with this much. So that's 1 minus alpha 1 times W1 plus G2. Then from this you get G1 star is equal to what? If you simplify, you will have this. Okay? And what about this case? So again, we have this much, and therefore in this case G1 star is just 0. Okay, so depending on whether this small G2 is kind of too large or not, we have G1 star equal to that or this, right? So just to summarize, so case 1 and case 2, they end there, and therefore player 1's best response, okay, and call it B1, B for best response, and that depends on 2's contribution to the public good, and it can be written like this. And concerning, I mean, if you're just curious about where should we have this equality, here at the bottom or at the top, so it doesn't really matter, because when G2 happens to be exactly this much, then if you plug this value into here, then you will see that this expression actually reduces to 0. Okay, so the bottom line is that it doesn't really matter whether you have this, or instead of that you can have, I'm sorry, you can have, rather than this, have something like this. It doesn't really matter, okay? But I will leave it as it was at the beginning initially, so I'm going to keep this form, okay? So to summarize, this is player 1's best response. This is the most important thing in this step, okay? And step 2, so step 1 was what? Again, find player 1's best response. And step 2 would be to find player 2's best response. Okay, so step 2, find 2's best response. And you will see that the argument is completely symmetric, so I can just switch the subscripts from this case, from this step 1. So 2's, okay, so I can write it this way. Similarly, 2's best response is B2, call that B2, and that depends on 1's contribution to the public good, G1. Okay, so now this is step 2. Okay, step 3. Now let's identify Nash equilibria. Okay, and how do you identify the Nash equilibrium? By putting these two best responses in the same space and finding their intersections, right? So, and for that, things are a bit tricky. So let me kind of try to be a bit slow about it. So first, let's try to plot this player one's best response. So okay, first of all, this player one's best response, most of the time it is like this, right? And when G2 is kind of too large, exceeding this value, then optimal G1 will be 0. That means, so if I put this intercept somewhere here, let's say it is here, so it is like this, okay? And once G2 above this threshold, then form 1's best response will be just the 0. So I will have this flat part. Sorry, a vertical part. Sorry. So we'll have this. Okay. And then after that, I will have what? A line of slope. So here I have minus alpha 1. So in this space, that will be the slope of minus 1 over alpha 1. So I will have this kind of curve. Okay. So slope is 1 over alpha 1. Okay. So that's for that is for player 1's best response against the G2. Okay. Now let's plot player 2's best response. Here now the question is whether G1 is larger than or smaller than this threshold, right? So let's put that threshold here. Let's say it is here, alpha 1 over alpha 2 minus 1 W2. Okay. And when G1 is larger than that, G2 will be 0. So we will have some flat part like this. And when G1 is smaller than that, G2 will be like this, and the slope will be minus alpha 2. So no, it doesn't look like a straight line. So let me draw it again. Okay, and this guy's a slope minus alpha, was it alpha 2, right? So now what we need to do is to put these guys in the same space. So by the way, this is 2's best response. So let me indicate that it's a B2 of G2. Okay, and so as I try to combine these two pictures into one space. So I'm going to try to superimpose this red graph on this picture, okay? And one possible case is that the red graph looks like this, and then this. Okay, so just as it looks like in these two cases. And here, what is noticeable about the configuration of these two graphs is that this vertical intercept is smaller than this vertical intercept, right? And it goes down like this. And notice that concerning these slopes, so remember that at the beginning, we made an assumption about the alphas. And what are they? So these alphas are all between 0 and 1, right? So what we know about this slope is that this is, I mean, if you disregard this minus symbol, so 1 over alpha 1, that is larger than 1, right? So it is steeper than a line of a slope minus 1. So I can say this is like this. On the other hand, this one alpha 2 alone is smaller than 1, and therefore minus alpha 2 is larger than minus 1, right? So you will see that always this curve, this part is steeper than this guy, as is shown here, okay? But what is not always the case is that whether this intercept is smaller than this guy or not, right? So this is one case. Another case is, so there are actually 3 cases. So let me put them all first of all. So here I have case 1, case 2, and case 3. And case 2 would be when this vertical intercept is larger than this guy. Then I would have, oops, let me draw it this way. This and then. Okay, and another case is that this intercept is so small, and then this graph becomes flat very early, even before touching this point. So that's going to be this third case. So I have a point here, and even with a line of that is flatter than slope minus 1, I will have this. Okay, and you see that in these 3 cases, in the intersections, I mean, for each of these 3 cases, the intersections are unique. So here we have one intersection, and that's the Nash equilibrium, and for this, the intersection is here, right? So that's Nash equilibrium, and here we're going to have Nash equilibrium at this point, right? So this is Nash equilibrium. And so the bottom line is, depending on which case we have, we're going to have different Nash equilibria, but in each of these 3 cases, we have a unique Nash equilibrium, okay? And I mean, to be super perfect, you have to consider all of these cases separately, but to simplify our argument, we're going to assume that the values of these parameters, alpha 1, W1, and also, what was it, this alpha 2 and W2, these parameters are such that we are in case 1, okay? And when would this be the case? Well, for this case, you have to make sure that this value is this value is larger than this guy, and moreover, this value is smaller than this guy, right? So we assume that case 1 holds, okay? And when would that be the case? Well, you should have this. So why is that? First of all, this one is this vertical intercept, and I want that to be larger than this guy, and that is precisely this much point. Okay, and how do you get that? Well, we have the graph for this b, this red. We have the equation for this b2, right? And given this much slope and this guy, we can figure out what will this intercept, vertical intercept will be, and this vertical intercept. You can calculate that it is actually equal to, it is actually equal to this 1 minus alpha 2 times W2, okay? And the second condition is that this horizontal intercept is larger than this guy, and this horizontal intercept is what? If you go back, it is this much, okay? And this, so that is this expression. And what about this? Well, that is the expression for this horizontal intercept, which you can calculate from this picture. Okay, so you will see that this is indeed true when case 1 holds, and if you rewrite these two inequalities, so if you rewrite these inequalities, what you have is we have this. Okay, and so one thing we have to note from this is that this will be true whenever the all the parameters are completely symmetric for the two players. So this will be true if alpha 1 and alpha 2 are equal and W1 and W2 are equal. Why is it? So if this is true, then this will just cancel out and we will have some alpha on the left, and this will be just 1. And we know that alpha is, the common value of the alphas is less than 1, right? And this one will be reduced to what? This will cancel out with this guy, so we will have 1 over alpha 1, and we know that it is larger than 1. Okay, so this is indeed true if the situation is completely symmetric for the two players. Okay, and for that, I need to now, what remains to be done is to figure out the exact coordinate for this equilibrium point. And I'm running out of time, so I better stop, and I will continue from here in the next class. Okay. All right, then I will see you on Thursday. Bye.